Hi folks, welcome to the next lecture. And in this lecture we're going to take an introductory look to trigonometric functions and then some basic maths associated with trigonometry, Pythagoras, working with the trigonometric ratios, etc. So just to take a look where we are in the grand scheme of things, we've looked at linear, quadratic, cubic, reciprocal, and now we're looking at trigonometric functions. We still have to take a look at logs and exponential functions, and then we'll be looking at some analysis of functions. Just some of the things we need to know. Simplest equation, y is equal to sine x or cos x. I'll explain what these terms mean if you're unfamiliar with them in a little while. Any of those. The general equation, y is equal to a sine bx. Typical curve for a sine looks like this. It's a waveform. So regular waveform, regular period. Period is the time between each wave, etc. One input and one output. It's a continuous curve, so there's no breaks in it. It continues all the time. Well, the line continues indefinitely. Sorry, it should be a bit more formal. Some examples: AC electricity. So coming out of your socket is a very pure sine wave. Light and sound waves. So anything you see, anything you hear is due to waves, energy waves. And then we have electromagnetic radiation, electromagnetic waves, TV, your phone, anything electronic that's connected to the internet, anything like that, you can be sure there's waves involved in that. Then on a natural kind of state, heartbeat, biorhythms, they're all waveforms. Seasonal variation, change in tides, stuff like that. So they're all subject to these trigonometric functions, waveforms, in a more simple form. How do we recognize them? It'll have the prefix sine, cos, or tan before the input variable. So y is 3 sine x, something like this. Omega is tan of 2 theta minus 1. So again, Greek letters will appear quite regularly, especially theta is used quite a lot, this one. I know you all know this from your Greek letter studies. Here we have beta is 3 sine 2 alpha minus 2 cos delta. Again, Greek letters predominant in trig. Like I said, the simplest equation and then the general equation. So, like I said, that's how you know them. Sine, cos, or tan in front of them. The input is usually an angle in this case. It's not just a value, it's nearly always an angle. So we're going to take a look at angles first. First of all, if we're labeling a triangle, capital letters are used for the angles, lowercase letters are used for the sides. This is set in stone. Don't mess around with this. So small letter means a side, capital letter means an angle. Once you choose a position, okay, if you say this is angle A, everything is labeled anti-clockwise from there. So B must be then in an anti-clockwise position to A, as is C. Note then, side A is opposite angle A. Side B is opposite angle B, and obviously side C is opposite angle C. So for this reason, sides and angles are often called side angle pairs, because the bigger the angle A is means the bigger A is. There's a direct relationship between the two. That's why they're linked. The sum of the angles, A plus B plus C, inside a triangle is always 180 degrees. And similarly, the angle B plus this angle I'll just call D D plus B is also 180 degrees. If we make a straight line from an angle, the exterior angle and the interior angle add to 180 degrees. To some properties of angles, when we're kind of where do we start and stuff. With angles we start at 0 degrees. So this is 0 degrees here. If you're sailing or on a boat or anything like that, that's 0 degrees. So just be very careful. We're talking about mathematical angles here, not in a navigation context. So just be careful of that. So we always start here. And then angles are always measured in an anti-clockwise direction from that position. So this direction is positive. So we could say this angle here looks like about 60 degrees. So that's positive from there. If you kind of mathematically end up with a negative angle, so say you end up with minus 45, you've done some calculation and your answer is minus 45. This doesn't make sense. You can't have a negative angle. It's like having a negative length of wood, or, you know, it has to be, an angle has to be positive. There has to be a definitive kind of angle between the two lines. It's always positive. But if you do end up with a negative angle, how we deal with it? We just simply mean the minus means we're traveling against the normal direction. So it's minus 45. It's 45 degrees in the other direction, in the clockwise direction. A more correct way to describe that angle is again to start here, but to take the long way around in an anti-clockwise direction. So in this case, there'd be 360 degrees. So there's 360 degrees in a full circle. So in this case, it's 360 degrees minus 45. So the correct way to describe the angle minus 45 is as 315 degrees. We won't come across it too often, but it's just something, again, you need to be aware of. This causes a lot of confusion. There's two measures of an angle. In the same way as if I went into a hardware store and wanted a length of wood, the same length of wood could be described in feet, or it could be described in meters. And most people have no problem with that. It's the same with angles. If we have this angle between two lines, it can be described with degrees or with radians. So it's the exact same idea. Don't let it put you off. It's just two different ways of describing the exact same thing. If we're talking about degrees, there's 360 degrees in a full circle, and this is quite an arbitrary figure. It's to do with the kind of Georgian way of doing maths, where everything had a base of 60. Time is another one with a base of 60. It's from the same kind of era. But there used to be 400 degrees in an angle. It's a bit arbitrary degrees. There used to be kind of different versions of the degree. There's 400 of them in a full circle. There's 200 of them. It's kind of settled at 360 at the moment. So 1 degree looks like that. It's a tiny amount. The other way to describe the angle is with radians, and it's a little bit more formal. It's more kind of an engineer's way of looking at an angle. And it says that, well, if I had a radius of 1 and then I made the angle, so both of these are the same length, but if I made this arc length here the same length as the radius. Now the arc length, guys, we're not completing a triangle. It's not a straight line. It's a rounded line, an arc. If we have this where the radius is the same length as the arc, that angle will be the same regardless of the size of the circle. And that angle is called 1 radian. There's 2 pi radians, so that's 6.28 radians in a full circle. Remember, with degrees there was 360 degrees. So this allows us then kind of work from one to the other. 360 degrees is 2 pi radians. Now, one problem with using radians, the letter to describe radians is capital R. But if we use that capital R, now it starts to look like 2 pi R, which is the circumference of the circle, which is a completely different thing altogether. So to avoid that confusion, you either say the word radians, you'd usually say the word radians when you're talking about it, but if you write it, you leave out the R. You just say 2 pi and say the word radians. You write 2 pi and you say the word radians. So that's something to watch out for. So now if we divide both sides by 2, 180 degrees is 1 pi radians. And again, I just write the 1 pi. So to convert, I'll just write that again. 180 degrees is pi radians. So now if I want to get radians on its own, if I want to convert degrees into radians, I want to say, well, what's 1 degree? Divide both sides by 180. And I get this. So to convert degrees to radians, we multiply. 1 degree is this many radians. So we just multiply. That's our conversion factor. So degrees to radians multiply by pi over 180. If we need to go the other way, if we want to get radians on its own, then we divide both sides by pi. And that's 1 radian. So 1 radian is this many degrees. So to go from radians to degrees, we multiply by the reciprocal of this. And that's how you go from one to the other. This is like your key though. This is what will allow you figure out, how do I get 1 radian or how do I get 1 degree. Start with this. 360, you don't need the radians. 360 is 2 pi. And then you can take it from there. So we'll take a look at a few examples. There's a few of these on Moodle, so you need to be fairly adept at this. It's just something, it's a skill you need to have. It's not something we examine in a huge way, but it's just one of the things you need to be able to do. So we start with what we know. Convert 60 degrees to radians. So 1 degree, I'll just start with 180 degrees is pi radians. So 1 degree, I always start with this way because then I know I'm doing things right, is this many radians. And now I can multiply both sides by 60. So this will give me 60 by pi over 180. I'll just write in the R just so you'll know that's what we're looking at, radians. And now we can cancel. 60 will go in there 3 times, 60 will go in there once. So now we've got pi over 3 radians. So 60 degrees is pi over 3. Convert 240 degrees to radians. Well, again, we had 1 degree is pi over 180 pi over 180 radians. So to convert to 240, multiply both sides by 240. 60 will go into the top 4 times. And 60 will go into the bottom 3 times. So 240 degrees is 4 pi over 3. You leave the pi. Don't get your calculator and convert it into 3.14. That's not what you do. With radians, you always leave pi. It's the most accurate way to describe it. Pi is a number. It's transcendental. It's like, we haven't come across it yet. but pi is a number that goes on forever and ever and ever. So as soon as you get a calculator to try and describe it, you're bringing in rounding errors. So that's that one. I'll just clear this off. I want to keep the answer. 4 pi over 3. Now we go the other way. Convert 1.3 radians to degrees. Well, 1, again, start with, this is pi radians. So 1 radian, divide both sides by pi. Just I'll write it again because it looks weird without it. Is 180 over pi. So now, 1 radian. Yeah, I'll just leave it as it is. I don't need to bring it around to the left. So now I just multiply both sides by 1.3. Sorry, so 1 radian is 180 over pi. So 1.3, multiply both sides by 1.3. And again, we'll just, this time you can kind of work away. We only use pi when we're describing radians. We don't use pi when we're describing degrees. So now we can get the calculator. So it's 1.3 by 180 divided by, make sure I get divided by pi. And that gives us 74.5 degrees. Finally, same idea, 1 radian is this many degrees. So I just multiply both sides by 2.3. 2.3 radians is 2.3 by 180 over pi. And when we do that, we get 131.8 degrees. So that's just how you go from degrees to radians and vice versa. Now we take a look at Pythagoras in a right angle triangle. The square of the longest side is equal to the sum of the square of the other two sides. So you might remember that from school. The main thing is to identify the longest side. The other thing, Pythagoras only works for a right angle triangle. So if you don't have a right angle triangle, you won't be able to work anything out with Pythagoras. C, the longest side, is called the hypotenuse. And Pythagoras' formula states c squared is equal to a squared plus b squared. Now when we get the square root of both sides, we get c is equal to the square root of a squared plus b squared. So it's really a case of just identifying which values you have. Do we have a, b, or c? You'll need two of them. And then you can compute the third. One thing though is Pythagoras didn't actually invent this. This knowledge has been around since the pyramids. Literally the pyramids were built using this knowledge. Especially the 3, 4, 5 triangle is a classical Pythagorean triangle. It works out really nicely. So this knowledge was around for thousands of years before Pythagoras ever came on the scene. It was just Pythagoras was the one who formalized it and made it into kind of a mathematical statement instead of just a little piece of knowledge that people knew that worked. Just to put a visual representation on it, we're talking about areas here in a way. We know these from our quadratics. So this is actually what we're saying is, here's the side A. If we made that into a square, that's a squared. And then here's side B. Make side B into a square, we've b squared. But the area of a squared plus b squared is equal to the area of the red square, c squared. So that's a visual representation of Pythagoras. It doesn't help us solve problems, but it might give you a little bit of a better picture of what Pythagoras is trying to say. Now we'll take a look at some problems. We'll use the formula. So first thing, I have two sides, so this is my longest side. It's vital you identify the longest side because that's what sits on its own. And really I'd prefer often the c squared is equal to a squared plus b squared formula because it allows us work easily from the start. So I don't know, so c squared is equal to 24 squared plus 32 squared. So now c, get the square root of both sides. And obviously this is going to be a calculator exercise. Squared plus 32 squared, and that gives us 40. So that's the length of our unknown side. Here's another one. Now be careful here, again we're starting with c squared is equal to a squared plus b squared, but in this case we know c squared, we know the longest side, and we know one of the other sides. I'll just call the other side 48 squared. And now we have to manipulate to get b on its own. So first thing, we'll subtract 48 squared from both sides. And then we'll get the square root of both sides. So 50 squared minus 48 squared is equal to b. When you get your calculator, so it's very important, don't just always write the unknown side. Don't always just call him c. That's what some people think, that the unknown is called c. The longest side is always c, and you have to work around that then. 50 squared minus, square root of 50 squared minus 48 squared. And this gives us b is equal to 14. Now sometimes you'll have to go to decimal places and stuff like that, so just don't always expect nice whole numbers. There's just our formula. So this is a question for you guys to try. I think you know the drill. Pause the video and have a go to find the length c, or the longest side. Here's another one then. Again, pause the video and have a wee go. So we'll keep going, but you'll need these skills in some of the later questions as well, so make sure you practice on Moodle if you're a little bit rusty with Pythagoras. And now we're going to take a look at the trigonometric ratios. These are sine, cos and tan. I mentioned them at the start of the lecture, now we'll explain them. If we take a look at an angle theta, here's theta for a small triangle. It's like the three bears, medium triangle and a large triangle. It should be obvious that the sides aren't equal. Obviously the biggest triangle has a lot bigger sides than the smallest triangle, but the angle is equal. Theta is the same for each of those triangles. And the reason for that is because the ratio between A and B, if I label each side A and B, A over B is the same for each triangle. Or A over C for each triangle, or B over C. So this is the beauty of the trigonometric ratios, is it doesn't matter the size of triangle. All that matters is that we know two of these three sides. So like I said, the sides aren't equal, but the ratios of the sides, A over B for this triangle is equal to A over B for this triangle is equal to A over B for this triangle. So that's what's crucial. And then the angles are the same. So once we know a ratio of two sides, we can compute an angle. And this is the basis of trigonometry. So we'll formally take a look now at a particular angle theta. So theta could be up here either, but we're taking a look at it down in the bottom left. In this context, the hypotenuse is still the longest side. We're still looking at a right angle triangle, so the same language of Pythagoras applies. But the side opposite the angle, if you can nearly see the angle, that's like an eyeball. Whatever side that eyeball is looking at is called the opposite. The side that's beside the angle of interest is called the adjacent, because adjacent means beside. And as I said, the longest side is the hypotenuse. So you always have to identify, in terms of the angle I'm looking at, what's my opposite, what's my adjacent, what's my hypotenuse. So if I drew a triangle like this, and here was theta, this is the hypotenuse, this is the opposite, and that's the adjacent. So just be very clear on that, that's crucial. Now, I can describe that angle theta using these two sides, the opposite and the hypotenuse. So I don't need the third side, I just need two sides to describe the angle, because you can always envisage that the third line just is a dotted line. If I use this pair, opposite and hypotenuse, that ratio is called the sine, the sin. So sine of theta is opposite over hypotenuse. If I use this pair, the adjacent and the hypotenuse, that ratio is called the cosine, the cos. And the cosine of theta is adjacent over hypotenuse. So these will always be less than 1, because the adjacent is the biggest side. The third ratio then is using the two that aren't the hypotenuse, the opposite and the adjacent. And when we use these two, this ratio is called the tan of theta. So that's all sine, cos and tan are. They're just telling you, I'm going to describe the angle using these two sides. You know, so for sin, it's opposite hypotenuse. For cos, adjacent and hypotenuse. And for tan, opposite and adjacent. That's all sine, cos and tan are. They're telling you which two sides I'm using to describe an angle. When I was in school, we remembered it using this little mnemonic. I used to collect them. I've been doing this 20 years. I had a big collection of them, and then I lost them when I moved office, and I never bothered gathering them again. So you might know different ones. SOHCAHTOA is the way they teach it a lot in America. Some Irish schools use that a lot as well. But just make sure you'll be able to silly, sine, opposite, hypotenuse, cos, adjacent, hypotenuse, tan, opposite, adjacent. There's lots of these mnemonics, so whichever one works for you, stick with that. And now we take a look at, well, how do we use this? How do we find the length of a side using these ratios? So here I can see, well, I don't know my hypotenuse. So I know nothing about this side, so I can't use sine or cos because I don't know the hypotenuse. The only two sides of interest are these two, and I have my angle. So my angle tells me this is the opposite and this is the adjacent. So I need to use tan because that's the one that links those two sides. Now in this case I know the angle of interest at 72. The opposite is x and the adjacent is 1.3. So now I need to solve for x. I need to get x on its own. How I'll do that is I'll multiply both sides by 1.3 to get this guy up and out. So when I do that, I have x is equal to, I'll just keep it on the same side. So I multiply the left by 1.3. And when I multiply the right, we know that that'll just become x. So finally we can say x is 1.3 by the tan of 72. Go to one decimal place, I think is what I'll usually be looking for in these questions. And now you just get your calculator, look for the word tan. You don't have to say multiplied by tan or anything, you just say 1.3 tan 72. Hit equals, and we get x is equal to 4. So that's the length of that side there. Now we'll take a look at another one. Find the angle x. These require a little bit more maneuvering. But first thing we say, right, well, there's x. What do we have? I have the opposite, and I know the hypotenuse. So opposite and hypotenuse. I don't know anything about the adjacent, so I can't use cos or tan. You'll usually only have one choice. So opposite sine of x is opposite over hypotenuse. The opposite in this case is 7. Remember, it's the angle side opposite the angle. The hypotenuse is 9. And now we're kind of going, okay, I want to get x on its own, so I want to kill this sine on the left. How we kill sine is use what's called the inverse sine. And it is exactly the same as, it's the inverse of sine. It's the same as division is the inverse of multiplication. Addition is the inverse of subtraction. Square root is the inverse of squared. Inverse sine is the inverse of sine. So just real briefly, I'll write it out once or twice so you get used to it. What I do is I get the inverse sine of both sides. And then we have sine x, and that's equal to 7 over 9. So now on the left, I have the inverse sine of sine. They cancel each other out. And I'm just left with x is the inverse sine of 7 over 9. And now you just get your calculator. Make sure you press shift or second function, and then press sine. So that's how you get there, 7 over 9. And when you get your calculator, then we just work out x. So shift, sine. Make sure the little -1 is on the sign when you're looking at the digital display. 7 divided by 9, close the brackets. And this gives us x is equal to 51.1 degrees. Look at another one. Find the angle A using our trigonometric ratios. So, well, what do we have in terms of A? Well, we have the adjacent to A and we have the opposite. We don't have the hypotenuse, so tan is the ratio we're looking for. The tan of A is the opposite over the adjacent. Remember, opposite is opposite the angle. So that's 17.5 over the adjacent. And now in the same way as before, I want to kill the tan. How I kill the tan is I get the inverse tan of both sides. So this is a new kind of inverse function that we can add to our collection. So we get the tan of A. So we've just got the inverse tan of both sides. Now on the left, tan and inverse tan kill each other off. And we just left with A is the inverse tan of 17.5 over 8.5. And now you just get your calculator and again just write your answer to one decimal place. Remember, press shift first and then tan on your calculator. If you're using a sharp, it's the second function button. They should really call it the inverse function button, but so now when we get our calculator, shift tan And this gives us A is 64 degrees. So that's how we work using our trigonometric ratios, and we don't really go too much beyond this, guys. We don't get into using the sine rule, the cosine rule. You might remember those from the Leaving Cert. We don't go that far into this kind of analysis. But you do need to be able to kind of move these around, given two sides, you should be able to calculate the third side and any of the angles. So here's a question for you to try. Calculate the side x using our trig ratios. So we say there's the angle. What do we have in terms of that angle? We have the adjacent and the hypotenuse. So what's the right ratio to use? Etc, etc. I'm not going to give you any more hints after that. Question 4. What's the angle B? And again, bring your answer correct to 1 decimal place. So now in the next slides, I have more questions for you to try. So just you can have a go at these. These are a little bit trickier, but it involves the principles we were looking at with Pythagoras and then with sine, cos and tan. So determine the angle B. So we don't have enough information in this bottom triangle, so we must work up here. So first thing you've got to do is use Pythagoras to work out that length of side there. Now once we know this side, I'll just call it A, or sorry, no, actually that should be side B because it's opposite angle B. So once we know that side B, that's just a small b, not a 6. Now we can work out angle B because we know the adjacent and we know the opposite, so we can figure out what the angle B is using tan. Or alternatively, you could, once you know this angle side B and this side here, 7, then you can use Pythagoras to calculate the unknown hypotenuse x. This little symbol in here, guys, means right angle. So both of these are right angles, which means Pythagoras and our sine, cos, tan ratios apply. So have a go for both of them, work out B. You could work out x first and then B, or vice versa, but the questions will be asked in this order. Go to 1 decimal place. And then here's another one. Again, this one's a little bit trickier. I won't give you any hints. Determine the angle A and determine the length of side C. So the first thing I'd be working out is this side here, which I'll just call side A because it's opposite angle A. That's the first thing you should work out, and I'll let you go from there then. So that kind of finishes us up for this part of trigonometry, and we don't delve any further into really the hard maths of trigonometry. Obviously it's a huge subject in itself, but for our purposes we're going to leave it there. In the next lecture we're going to take a look at those waveforms I mentioned at the start, the trigonometric curves. So thanks for listening, guys, and we'll chat to you shortly.